now that we have our camera and ray implemented, we can move on with tracing some rays. So before we're adding random colors here, which is something that we definitely don't like. So we're going to replace this, all of this actually, with a function called update pixels, which basically what it's going to be doing is it's going to be updating this bitmap like this, and then this bitmap will be passed to the new view. So let's create this function. So it's going to be fun. Update pixels. Perfect. And here we're going to have very similar things. So we're going to start with file calls. Obviously, we do need an int array for our colors. So it's going to start empty, but with the size of screen width times screen height, just as before. And just as before, we're saying we need to update each pixel. So we need to iterate the same way that we did before. So we have X and Y. That's 0 until screen width. And then here we have Y, again 0 until screen height. Okay, but now we're not going to have random values. In fact, well, we're going to fill in the same values. But how do we do this? Well, we have rays, and if you remember correctly, if you remember before, our camera is capable of generating rays. So we have created our camera up here. Basically, I've created a camera because we have a camera object called cam. The position, so its origin is going to be 0 on the x-axis, 0 on the y-axis, but -5 towards us on the z-axis. And basically, it's going to be pointing towards the screen, basically. And that's why we have this nice flow through. Then here, we pass screen width and screen height, so nothing complicated. And that's it. So here, in our update pixels function, we're gonna have, our camera is able to generate rays. So we're gonna say ray for each pixel, basically. And this is gonna be ray cam dot generate primary ray x point y. Nice and simple. Now these are expected to be floats, so I have to say to float, but that's okay. And finally, we need to write to this calls value for our color. So it's going to be this times screen width. It's just as before. That's how we index it. And very simply, it's going to be the color that we want. So how do we get the color? Well, we're going to have a function called trace ray that takes our ray and something that we're going to call max depth. So if we have rays that bounce, for example, we have a mirror, then we're going to have to cast another ray from wherever we hit the mirror. So that means that we're going to have depth in a recursive manner in this case. So I'm going to go up here. We're not going to use this for now, but it's going to be useful after because we're going to actually implement mirrors. And I'm going to say 5. Cool. So now, after this for loop, or this nested for loop, we're also going to write to the bitmap. So we're going to say bitmap set pixels calls 0, same as before, no difference. 0, 0, and screen width and screen height. And that's it. That is our update pixels function, but we do need to create this trace ray function. So I'm going to remove all of these because we don't need them anymore, including this. And let's implement our trace ray function. So, okay, this is going to be a function that again takes a ray and it takes the depth. That's going to be an int. And it outputs an int because remember our colors here are ints. Cool. So this is a nice function, but what exactly are we tracing the ray in? Well, we need to somehow, we need to add primitives to our scene. So the way we're going to do this is, all we need to do is we need to describe things. So what that means is, if we say this primitive shape, which might be a sphere, it might be a triangle, it might be a torus, it doesn't matter, is there and has these properties, the ray should be able to see whether it intersects it or not. And then we move accordingly. Currently, though, we don't actually have a shape. So we're going to go here, and we're going to create a nice primitive, which is the sphere primitive, because we like spheres. So let's start with what describes a sphere. The first thing is, well, how big is a sphere? So we have val radius. So what is the radius of the sphere? That is just a float. Then where is the sphere in the world? So we have a val center, I'm going to say. So that's going to be a float 3. See, float 3. And then if you remember correctly, if you remember from before, our array here is storing an object index. So we want to store an ID here. So that's val ID int. And that's it for now. Later, we're going to add materials for each of these. So whether they're mirror, for now, mirror or diffuse. But for now, I'm going to keep it like this. So we need two functions to see whether we hit the sphere. Well, we need one, but two functions are relative to this primitive that we call a sphere. The first one is, did the ray hit it? And so we're going to have a function called intersect that only takes a ray, very simple. And so I'm not going to go and describe the math behind this. I am going to provide a link. The math is actually quite simple for a sphere, but just to keep it simple and basically ray tracing only related, I'm going to just not mention the math. So we start with this vector called OC that you might already figure out comes from the center to the origin. Yes. It doesn't like that. Oh, oops. And then we're going to have a parameter called B that is going to be OC dot ray dot D. So basically we start with the OC, which is just, again, centered towards the origin of the ray. Then C, which is going to be OC dot itself minus the radius. And then our most important parameter is going to be the parameter T, which starts as B times B minus C. And then our var D, which is going to be B times B minus C. Cool. First of all, we're going to say if D here is smaller or equal to 0, then we return. Basically, we didn't hit it. If we reach this point, we're going to say that D is the square root of D. And you may or may not already be seeing why this math is done. T changes like this, and then we finally reach the point where we're seeing whether we hit our sphere. So we have var hit, which is a Boolean. I was going to say, well, if T is smaller or equal to ray.t, which starts as infinite, and T is larger than 0, because that's important. And then we're going to say hit. So if we hit something, or hit the sphere, then t will become t. So the length of the ray will become this t, and the object index will be the ID of the sphere. And we return. Now, if this hit is not correct, we can go here and say if c is larger than 0, then return. Cool. But if we keep going, we can say d minus b. So you can see this is different than this. And here the hit now will become equal to t smaller or equal again, right, dot t. So the new t is compared larger than 0. And then again, if hit, we do the same stuff. That's t, and ray dot object idx equals id. And that's it. So this will be able to, so we check whether we hit something, in this case the sphere, if we have a change the object idx of the ray and the t of the ray. So one more function that we're going to need, not now, but in the future, when we hit something, we want to know what the normal to that intersection point is. So triangles obviously have specific normals, so they are simple. But spheres themselves don't really have normals, but the normal to a point is easy to find. A point on the sphere, that is. So we can have a function called getNormal, and you're very likely figuring out what this is going to be. It's going to return a float 3, obviously. Quite simply, well, we hit a point on a sphere. So if we want a normal towards that point, all we need to do is draw a vector from the center of the sphere to that point. And conveniently, we have this, when we have array, we can say array dot, oops, we need to pass the array here. When we have array, we have this array dot intersection point, which is going to give us the intersection point. So then all we have to do is say, well, var, let's call it norm, is going to be I minus center. So the point from the center to I. And remember that we do need to normalize it. Very important, because else it's not going to be a normal. Then we return the inside backside check. Remember that we had this in the utils here, this thing, to make sure it won't really matter here, but if we have dielectrics, it matters a lot. So it will know whether we hit the thing that we think we hit. It doesn't matter for now, and it doesn't require much explanation. But the point is we return the normal. All it will do is flip the normal. So that's it. Cool. So now we have spheres. Let's create a few spheres here like we created the camera. So let's say var, that's going to be val, sp0, I'll say sphere is sphere, and the radius, let's say it's 1, which should be enough. The position is going to be 0.0f, 0.0f, and let's say 5.0f. in terms of depth, so away from the camera by 10 units. And then finally, the ID is going to be 0. And because it's fun, I'm going to create 2 more. This one is going to be SP1. And it's going to have the same radius, but it's going to be at x minus 5. So it's going to be to the left. The ID is going to be 1. Then SP2, which is going to be at x5. So it's going to be to the right. And the ID is going to be 2. Cool. So now we're going to move on to the trace ray and implement it. Well, first of all, because we said depth, we're going to say if depth is smaller or equal or smaller than 0, return. Color, if you say color, by the way, this is a library. any of these, they're ints, so they're already there, ready for you. You don't need to use the conversion thing that we used here, the RGB32F to RGB8. They're already going to be RGB8 things. Cool. Okay. So here we need to see whether we hit something. So, okay, that means we have to check whether we intersect any of these points. So for each of these primitives in our scene, we need to run the intersect function. So for SP0, for SP1, and for SP2. Cool. Okay, so if you remember, when we intersect something, we change the object IDX and we change the distance, so the length of the ray. So based on that, we can glean whether we hit something. In fact, I can say here, if ray.t is smaller than, oh, we can just say if ray, let's say that here we missed. So ray.t is either equal to 130f or ray.t or ray.object idx equals -1. So then all we do is return black in this case. Generally, if we miss, we're going to be sampling like basically a sky dome. We're going to actually implement a sky dome, but not for now. Here we're going to say if, so we didn't miss at this point. So we're going to say if ray.t, no, why not? So if ray.object idx is 0, or let's say, just to be a bit more clear, sp0.id, then return, I'll say color.shean, and we're gonna actually add 2 more of these. So we're gonna say, okay, we else if. So the good thing with this intersect thing is it's gonna return the one that is actually closest to us, which is nice. So this is going to be 1, this is going to be 2, and I'm going to say the one on the right is on the left is going to be red. This one is going to be blue, not black, blue. And believe it or not, well, that's it. Am I missing something? Oh yes, let's have a return color.black here in case we ever reach this point, because else it's gonna yell at me. So now I should be able to see 3 spheres on the screen. There's 1 sphere in the scene, which is kind of interesting. Where are the other spheres? Why can we only see 1 sphere? It's too big. Let's say to put them too far away on the x-axis. So yeah, okay. They're off the screen basically. So if I add 2 more, there we go. We can kind of see them now. And you can see I can actually give them depth a little bit. So I can say this is 6 and 6. So they're a bit behind that one, because 1 unit is pretty significant, it seems. Yeah, and you can see what it looks like. So this is actually now ray tracing. Cool. So what we're going to do now, next, in the next one, we're going to actually implement direct illumination. So instead of just considering everything to have a color, specifically like here, we're going to, well, they're going to have a color, but we're going to take into account a light, because in real conditions, we're going to have light. So we're going to use a very simple light. So there won't be any sampling. It will just be a point light. And based on whether we hit the point light from a point, we're going to cast shadows or not. So that means that we're also going to get some hard shadows, which is extra nice. So that's going to happen in the next one. See you then.